said that they should go find objects above a certain size that would hit Earth and a certain number, a certain fraction of them. And they didn't do it. And then people from the university said, well, we really want a big survey telescope for looking at astrophysics and where things are, but we could find a large fraction of these objects and very small objects to make sure we see where they're going and see if these things would hit Earth or not. And I won't tell you much more because we have an expert that helped us develop this whole system here. And so I'm going to introduce Sifan Kahale. And Sifan graduated from the University of Wisconsin with a degree in chemistry. So our last speaker was a biologist. And Sifan is chemistry, and you'll hear about me later. And it's also not astrophysics. And performing research for the university hospitals, she was instrumental in developing 2 of the analysis procedures of the first commercial automated clinical analysis machines. She then started and was the CEO of a small corporation that designed and manufactured what we now call PCs. These were used by the university for clinical chemistry automation, and it launched her career into computers and IT, and eventually becoming the director for an international training division, having classrooms in over 20 countries around the world. In fact, her name was given to her in Beijing. She's always been involved in astronomy, having built and fully automated a number of her own telescopes from scratch. And today, Sifan handles the summit and control room computing for the STARRS telescope, is a member of the UH steering committee for our virtual classrooms and outreach, and is one of the observers for the STARRS telescopes. She's responsible for the IFA's virtual presence in numerous online worlds. And this should be a really interesting, this is a unique instrument. There are no other telescopes quite like it. This should be an interesting talk. So please welcome Sifan Kahale.
Thank you.
And you're okay on lights, I think? Like
yes,
okay.
This is great. I think everybody can see it okay. I don't have any very beautiful shots like Gary just did with the sand. I wish I did, but you know.
And you want questions at the end, or
at the end? Okay. Yes, please, because it's very short with what we're doing here. And like all of our talks that we give here, they're all video cast both to the web and also to virtual worlds like Second Life, InWorlds, Metropolis, and a number of other ones. And so one of the things I had better do is say hi to my virtual audience, because they never see me up here. They just, I'm in worlds with them talking and chatting, but they never have seen me live before, so hello. Or I should say aloha. So I started about 8 years ago here with the STARRS Observatory. You know, as Joe was saying, the main purpose, well, actually, in the very beginning, it was put together by a consortium of about 12 to 13 different organizations around the world. Each organization came together and proposed a main mission. And out of that, it reduced down to about 12 of the 12, reduced down to 6 major missions. One of those was a survey of the entire sky, the entire visible sky that we can do here. Every time you do, say, take a complete picture of the entire sky, you call that an epoch. We are on epoch something like up in the 20 billions. The unique thing about this, that this brings along, is sort of a new, different area of astronomy called time domain. And what's beautiful about this data that we now have collected for all these years is if something goes pop tonight, let's say we have a supernova, and by the way, we're detecting them about once a night. Let's say we have a supernova that goes off. Well, what was that beforehand? Was it flaring beforehand? Was it brightening and dimming? Was it doing weird stuff beforehand? Or was it just sitting there? Up until STARRS came along, you couldn't ask her that question. Because the second the star went boom, everybody goes, oh my goodness, there's a supernova out there. Everybody shifts their telescopes over to it, takes all the data and images from it. But they can't go back in time. So what we have compiled, and by the way, our databases right now, the complete index of everything we have is close to 3 petabytes. A petabyte is 1,000 terabytes. So to give you an idea, that's one copy of our data. We keep at least 3. We're building a 4th one right now because we're about to move our compute facilities over to the Big Island. So we're having one that we're going to keep right here. So there's a lot of data. And as a number of people have said, there's gold in them thar data. And that's just one idea, one example of how scientists are using this data, that we're creating. So of all of these surveys and missions that they came together, the 6 major missions, a couple of them were the sky surveys that we're doing. None of those were actually looking for NEOs, near-Earth objects. Those are asteroids and other things that are going to hit us or come close to us. Okay, but it turns out that when you're doing this survey, and here's the unique thing: it's not just a survey; it's a repetitive survey. So that way you can a picture from tonight, and take the same picture tomorrow night, and then subtract the two. If you subtract, remember, stars and the image, everything's numbers, right? So you have a star of a brightness of a certain amount, and you subtract tomorrow's image, a star of the brightness of the same amount, it's going to go 0. So anything that's relatively stationary is going to go away. So what's left? Things that move, because you have a spot where it was today and a spot where it was yesterday, and I'll show you some slides of that. And so right away, aha, we've got something. And the second thing that might be is if something brightened, supernovas, right? Or if something dimmed, maybe an exoplanet or something going in front of a star, okay? And I can go on and on and on. So this is a beautiful engine for finding these kinds of things. And like a story I always tell when people ask, our job, well, then you get excited and you follow up and all this. No, here upstairs, we hardly know, because this all takes place with a tremendous amount of processing that goes on down in Kihei. In fact, I've got 32 racks. Each rack is a little bit taller than I am. Each rack holds, maximum is about 42 computers. Each computer has about anywhere from 8 to 32 cores, CPU cores in it. Do the math. It's some huge amount of processing cores. And then in addition to this, all the data disks that we have. Some of our computers hold 48 disks. Each of those disks is now 6 terabytes. So it's massive. It's huge. It's called a data processing pipeline, the IPP. Okay, the imaging processing pipeline. Now, in computer terms, a pipeline is something where you take something in the front end, and you need to process this in such speed in order to get it through. In our case, because the next image is coming down line. So you need to do this in a quick enough amount of time so you don't have time really to save it on disk. You can't take it into one computer, process it, save it, and the next computer takes it up. No. It's flowing from processor to processor until it comes out the back end and is saved. Even with this, they will start, in fact, we've just opened up, so the telescope's open, it's taking images right now. And when you're done, you can go up you can go up and see Angie. She's the observer tonight. I get to go on tomorrow night. So, the IPP is now opened up, and it's receiving these images that are coming down from us right now. And it's going to do this all night, and it's going to take until about 2 or 3 o'clock tomorrow afternoon for it to be completed. So it gets like a couple hour rest, and then boom, off it goes again. So it's very fast, very huge, a lot of compute power, and that's down in Kihei. So with that in mind, let's take so we're watching for these things. Now this is a bit of a scary kind of picture, but I think it was sort of cool. My boss, Ken Chambers, found this one. I thought it's what he uses for his. This is the top of Haleakala. This is the erosional feature. Can't call it a crater because it's not a crater. This is the ridge coming up from Poli Poli, and this is an old shot, but this is Pan-STARRS right here, at the edge. Right here is the park headquarters, and or the park, the park at the very top. This is Red Hill, where you go up and you can circle around and see things. And we normally the winds are coming from this direction, so we're aiming our telescope off this way. So when we open up the telescope, we see all these people over on Red Hill looking back at us going, as our dome slowly opens up. And yes, we have cameras all over the place, that are in here. I'll tell you a little bit more about that too. So that's one of the, you have to look, one of the requirements for operating remotely, which is, as any observer will tell you, is that a blessing to be able to sit up here in a nice warm office where you can have the lights on, you have a kitchen, restroom facilities, everything else. Whereas at the summit, when in fact, that was my first task that was assigned to me. In my background experience, I've consulted for a number of top 500, Fortune 500 companies in how to put together robust, what we call production environments. In other words, 24/7. Anything goes wrong, something else takes over, etc. Right? And so I was hired on to do two things, when I first came here. One was to take this engineering project, this university project, and operational is sort of a foreign word. Right? So it's to take that and make the changes and everything else is necessary so that this can continuously run. And this is 9 years now that it's been going. So, and the second thing second task I had was to automate it so that we could run it down here. To make sure that I was motivated, they made me an observer. So I had to sit up here, and let's see if I've got the next here. I had to sit up here in this building here. This building is, I think there's probably more holes than so the wind goes right through you. So can you imagine 14 hours a night in this freezing building? You can't turn on the heat because hot air is going to rise and get in the way of the telescopes. You can't turn on light because where the wind's coming through, the light is going to go the other direction, right? And you have to stay there for 14 hours in this dark, very cold night, especially in winter. I think I probably automated it in record time. Talk about motivation. I was very, very motivated. So we have an observer that just went on for something else. That she moved on, and so now they've put me back into service. So that like tomorrow night for 4 nights I'm going to be I'm observing again. But at least that's here. And you're welcome to go up and take a look at our facilities up there. When you're done. Let me go back one. This is we're a survey instrument. In other words, our job is not to look at anything specific, but to go across the sky and survey. And I usually explain this to people when I give tours and things as imagine back in the old days of the cowboys and the Indians. When you had the troops go out, okay, they had scouts that went out in front of them. Okay, the scouts do not engage the enemy. They get wiped out. Right? We're the scouts. Okay, so we're out there, and our job is to keep looking. If we find something, it's not for us to go back and look and check. We're going to miss something else. So our job is just to keep going and sort of throw it over the wall, kind of, so to speak. And so I always say the big boys on the big island with the big telescopes, they take it over from there, as well as other places in the world, and then track down whatever it is that is interesting within our data. But our job is to keep going. So it's a survey, and it's a panoramic, and I'll talk a little bit about that here too. And the rapid response. And what that means is that when we find something, we can immediately alert the world, and they can train their eyes, ears, and scopes in on that and see what's going on. And a case in point on this is supernovas. Because of us, the book on supernovas has been shredded and thrown out. Sorry. It used to be you'd find 2 or 3 supernovas a year, and it was usually found by amateurs, because the professionals are all looking at certain places in the sky and doing their research. And it's the amateurs that are out there, standing and says, "Joe, look at that. Is that supposed to be there?" So I don't remember thinking. Joe says, "No, I don't think that's there either." And then they'll call in some friends the next night. You know, and they all goes, yeah, no, we better report that. So they'll call like the police. I'm serious. And then the police will muddle around, well, you know, who to report this to? Eventually it gets into some, you know, academia someplace, and they'll report it, and then they go and there's a supernova. And then the guy that first saw it, it gets, you know, his name on it. And that was a very huge thing. Now, when a supernova goes off, it's a huge, bright explosion. And you can watch the different wavelengths of light that are coming off there, and it tells us things about what's going on in the cloud as it's moving off, in what we can extrapolate back and what's going on, you know, in the first place. And if you think, you can see it like this. You see these light curves that are coming off, you know, and then they slowly die out over time. Well, because of this, all we were seeing, because it's like a day or two after, all everybody was seeing was the light curves going down. Pan-STARRS came along, and instead of 2 or 3 or 4 a year, we're finding one a night. And not only that, we find it, report it right away. They don't go boom and come down like this. They go boom, then go down, then another huge bump and come down, and then another one and come down. And the mechanism that's doing this, totally unexpected, you know, in what's going on in a stellar explosion. And it told us an awful lot of the dynamics inside the star as well as within its environment. And that's just one thing that Pan-STARRS did, or I should say the data from Pan-STARRS allowed to do. And that's part of this rapid response, to be able to get this information out there quickly so that the big boys in the big island with the big telescopes can turn around and take a look at this and get more detail out of it. So that's just one example of what we do. Now, there's two. There's a Pan-STARRS 1. This has been in operation science-wise for about 6.5, 7 years. Okay, it was constructed probably about 12 years ago. It takes that long to build these. The actual physics, just like the Deca stuff there, it takes a long time. Actually, it doesn't take too long to put the structure and the mirrors and everything else together. Then it takes a couple of years just the science team to come in to figure out, what do we have? When I point my telescope to this star, and it's not pointing at that star, why? What is it? How much do I have to compensate the motors for? When you tilt a telescope, you know, it's the tons of glass, and that's going to deform on itself. How much do I have to push back on the actuators to make it round or you know, get its figure back, kind of a thing? All of this, yeah. All of this has to be figured out. Okay. There's a lot of stories I have, but I'll save them. I have a story about there's a 25-term equation, cosine of this minus sine of this, and it's 25 terms long, and it takes into account the trusses, the temperatures, everything, you know, for able to do this. And it was John Tonry and can't remember the other guy's name, but they were up there with myself and Bob in the telescope, and they were having this really, I mean, Nick Kaiser, yeah, they were almost at fisticuffs. They were almost going to have a fight. They were just, and sort of this way anyway, but they're really arguing, and they're arguing this 25-term equation. Now, mind you, and I mean mind, can you imagine keeping that entire 25 terms in your head and what each term meant, and then arguing it? That's what they were doing. You know, Bob and I were looking at each other. Whoa. Okay. Finally, one of them stops. I think it was John. And then the other guy stops. And silence for a little bit, and he says, I know it is. In the 21st term, that's supposed to be a plus, not a minus. And you want to know something? We've been running ever since. That was it. You know. Of course, Bob turns to me and elbows me and says, I could have told him that all along. I just wanted to see how long it'd take him to figure it out. Says, okay, Bob. So now we're not the biggest telescope on you know, around. We're a 1.8 meter, but it's big enough for what we need to do. It's specially curved. I mean, its curvature and its figure is very special because what we have underneath here is a 1.4 gigapixel camera. the world's largest digital camera that we're allowed to know about. Okay, I am sure the boys next door to us have some larger things hidden around. But anyway, as far as the world is concerned, this is the largest digital camera. And it's got a sister, which is going into the second telescope, the second Pan-STARRS, which hopefully is going to be up and running here in a couple of months. So we're very, very close to going into commissioning with that. So one of the biggest things about this is that it's got a 3-degree field of view. In other words, most telescopes, this is sort of built opposite of most telescopes. Most telescopes, you build them so that they look very, very far into a tiny spot. Can you imagine take a survey if you're looking just at one little speck? You can't do it. So we wanted to take a large volume of sky at a time each time we took a picture. But you lose resolution with that. So you make it up by having the world's largest camera. So what do we have? We have the world's largest wide-angle lens camera, right? So it's very, very special. It was very hard to get this together and flat all the way across. If you remember taking a look at wide-angle pictures, you can see the vignetting, on the side. We can't have that, okay? So we have massive corrector lenses and everything else to get this field flat all the way across. That is what took so long.
Well, I think since our fourth speaker is nowhere to be seen, we can both go. I'll go a little longer, and you can go a little extra.
Good.
Too.
Okay, thank you. I was wondering about that. My stories always.
I think he's not here, so you get a little more of that.
I get a little more. Okay. Oh, that's good. Okay. Now.
Unless he shows up.
Then I'm in trouble. Then I have to really.
So it's up.
Okay. All cameras are black and white, even the ones you have. But they cheated. Instead of in front of each of your pixels, they painted a little red, one of them red, a little blue, and a little green. And so they read in 3 pixels, and then they form the colors out of them. Okay? And so if you have a 9-megapixel camera, you're going to get a 3-megapixel picture. Right? We can't lose any of our pixels. Every pixel is precious to us. Sounds like a saying that should go on the wall. So instead, we have filters. We have these big filters that we throw in across the camera. So if we want to take a color picture, we have to put in a red filter, take an image, put in a green filter, take an image, put in a red, put in a blue filter. Okay, combine them and then get our image that way. So we can't take a picture of anything that's moving fast. Okay, this is interesting. 0.5 gigabyte of data per second is right now streaming off that mountain down to our computers in Kihei. After this pipeline gets done with it, that 0.5 gigabyte turns out to be 7 times larger. 3.5 gigabytes of data is what we produce out of that image that's in there. And I love, they call this the reduced image. 7 times more that's inside of there. Okay. So some of the major projects, that was what we were doing before, was this consortium. Now we are primarily funded by a couple of places. The majority of our funding comes from
we're going to start
NASA,
that just in a few minutes. We're giving it a couple. It looks like our fourth speaker's not
and
here.
Actually, the first
number 2's
top
going a little
4
longer,
of these
and number 3
are
is
all
going to take
pretty
up some
much
extra
come
time.
out of
but
doing a search for for asteroids.
Cool.
It's still the survey. It's still a survey.
Okay.
We're scanning huge chunks of the sky.
I am.
But in so doing, we're not just
Let's see. I'm
again,
just going to do a quick once
capturing
around
asteroids,
here and see how we're doing.
but anything else that's out there that's moving, okay, or doing something strange. So near-Earth objects, those are asteroids or things that are their orbits are coming
close. You can come in
to
a minute if you want.
It doesn't necessarily mean that
be over in a couple
near
minutes.
us right now, but it means in time they're going to be, and therefore we better watch that.
JD?
If they're a little too scary, then we call them a potentially hazardous object. Okay?
So,
and those are ones where they're not necessarily going to hit us, but they're coming so close that we better watch them very carefully.
We'll ask you to funnel people in
now,
as we open them up. Okay.
Just because you find one of these once,
apparently a lot of people in there,
book.
or a lot of people out here have no idea where the talk is.
Everything in space gets
so
perturbated by everything else.
Okay.
including if it's a PHO, it's going to
See
come
my
close
friend.
enough that it'll be perturbated by
Get
the
a good
Earth's
picture
gravity.
with a close-up
gonna
of
change its orbit.
these, right?
So we find
Or
these.
even while I'm lecturing. Right?
We have to keep tracking. Because today this might be what their orbit looks like. But the Earth, the Moon, other things that they're going to pass by or go by could change their orbits. Okay, so these have to be watched to see what they're doing over time and if they've changed and have they become really hazardous. Okay, so potential PHOs and NEOs. Also, we're looking at anything that's in the inner solar system and outer solar system. We're finding a lot of what we call planetoids and other objects that are close in. Comets, I think we now have, we can claim 50% of all comets that are found in a year, we find them. Amateur astronomers are really mad at us. I'm an amateur astronomer too, so I don't like that. But, you know, because of the survey, all of these things are popping out.
What do you think you have, maybe 10 more minutes?
Okay. Yeah, I should be able to do
Okay,
that.
I'll be back.
Okay.
Sorry to interrupt.
Yep. Supernovas, type 1As. This is a special kind of a supernova, of a stellar explosion. And it goes off in a unique way in which we can use the light from it and other features of it to determine precisely where it is, how far away it is. Okay, by looking at redshifts and other things. So this becomes what we call our standard candles. So one of our surveys today is we do a supernova. Well, there's a number of supernovas that are out there that we're watching. And so we camp out with the telescope and just take picture after picture after picture in different filters, you know, and so we get information about that supernova. And this is building up and refining our yardstick to the stars, okay, for everybody in the community. As an observer, we sort of hate supernovas because the supernova observation takes about 8 or 9 minutes to do this, which is barely enough time for the observer to type everything in, to get everything ready, and then the next one is on top of us and says, oh, no. So you get 4 or 5 of these in a row, and you're underneath a table, and your keyboard is smoking, and you're blowing on your fingers. And whereas our normal chunks, when we're doing surveys of the sky, a normal chunk is anywhere from 30 minutes to about an hour and a half. As you can imagine, as an observer, we love those. That's enough time. Also, you might have heard of LIGO and gravity waves. We're part of both this and neutron detections to find the progenitors. So we go and search that particular area where they think it might be and see if we can find something, you know, for them. So we're also part of these as they come up. This is, JD just left, this is one of his favorite. He got me this. This is an example of time domain astronomy. This is looking at the galactic core. And in a second here, you're going to, once my computer decides that it's going to actually run. Come on. What we are doing is we're zooming in at the very core, and we're going to watch, this is actual live data. These are stars over time, and you're going to see these move. Okay? I hope. 15 years. So it's one of the first times that we were able to, let's go back. Getting back to, here it is. Let's see. So we're going to zoom into the galactic core. And then we're going to watch stars orbit. Now, we know there's a black hole that's in the center. You can't see the black hole. But it really doesn't want to do this, does it? But you'll see these circling, you know, this object. And okay, and you know, yep, I'm going to go on. But it was very nice, you know, to be able to see this. Oh, here it is. Okay. I talked primarily about this data coming from Pan-STARRS to the IPP, and then from there it's analyzed, you know, by our scientists and controlled from here. These are the filters that I was talking about, you know, that go in, 6 different filters. Each filter is multiple of millions of dollars, you know, to get that kind of glass. This is our shutter, And just to show you the size of it, they put pineapples in there. From that day forward, for 8 years, it's known as the pineapple slicer. You know, these are the chips that are inside, our camera. So this is the world's largest camera. And just for perspective, that's the mirror that goes on top, or the lenses that go on top of this. So you can figure that's about this big. You know, it's a huge, huge camera. Again, that camera is right here. So it gives you a perspective of what this looks like on the scope. The scope is leaned over this way. Okay. And I'm not... This is the moon. This is a typical picture that we would take. So it shows you the huge field of view that we have. Here's our center. This is upstairs. You can go upstairs and see 16 monitors. It gets very warm up there. And let's see. This is the area of the sky that everything in black is what we view on a routine basis. This is the galactic plane. There's too many stars in there for us to be able to detect things move or change. Yeah. Okay. Okay. Yes. So I think this is the end because I can't, just some pretty pictures. Yes, yeah. These are all taken by our camera. It took, I think, 167 images to put this one together. You know, you have to take an image again in each of the different colors, enough of them to stack together to get it crisp, etc. So about 167 images to do that. And this is... I would love to do that. Thank you. Thank you.